Yes, presentation for Kenan Muric, which will explain us the pain of generating complete and compliant Nexus files for dynamic setups.
Yes. Well, we will be focusing on taking the pain out of the generation of Nexus files. So a bit about the agenda. I will give a brief motivation to why we do this and how we solve this problem is through the Nexus Constructor. I was planning on maybe giving a live demo, but considering the technical issues we've had so far, I'm gonna just show some slides with examples of how you use the tool, basically. I will also talk a bit about components and component geometries, which can be quite tricky sometimes. I will also describe the file writer modules we use at ESS to stream data, serialize and stream data. And in the end, a summary of this presentation. So as we can see here, the motivation. So at ESS, we are using epics for low-level control of devices in the instrument setup. So everything from choppers to slits to motors area detectors will use the epics layer. And on top of that, we are using Nikos as a network-based control software. And all the controls that user will do will be through Nikos, through the command line, through scripts, or through the UI. And the Nikos will also be deciding on when to save data from the experiments, either script-based or from a command line. And basically, we are using Kafka to stream all data. And that data that's streamed through Kafka is serialized using flat buffers. So the Nikos will essentially be, and the devices will be the producer of these messages. And eventually we will have a file writer that we call Kafka to Nexus, which is developed at ESS to write Nexus files. And eventually it will end up in a data storage. And we can use Skip or Jupyter notebooks for data reduction and processing. So the file writer in itself won't be clever enough to use the Nexus standard to define the complete data structure. It will depend on the experiment. It will depend on the instrument. So we need somehow to provide this information to the file writer. And the approach we have used is to provide that through JSON files. That defines the complete structure of the data file. And that's also sent through Nikos as a Kafka message. And the file writer will listen to the sync broker and topic and essentially retrieve the structure and generate a file based on that JSON configuration. And to generate these Nexus templates in JSON, we decided to develop a tool for that called the Nexus Constructor. And just to give a brief example of a Nexus file that we usually will write at ESS, those of you who are not familiar with the Nexus file format, it's basically HDF5 files with some additional constraints on how they're structured and how you use attributes as well. But we can really differentiate in a couple of sets of data. So first we'll have some groups, Nexus groups with corresponding Nexus classes. We have static data. Static data, this essentially all data we know beforehand before we even start saving any data. For example, experimentize all who are the users in the instrument. And on top of that, we have the dynamic data, all the detectors, all the motors, all the choppers. And for each IOC, we also, in Epics, we also have an alarm system. So also that needs to be stored in these files. And on top of that, we also need to know where stuff are in the instrument. So we add transformations, both dynamic and static, to this Nexus structure so that we can understand when we analyze the data, where is the chopper, where is the detector, it hasn't moved, and so on. And at the TSS, our main goal is to comply with this standard as much as possible in the Nexus standard specification. And just to give like a brief example, the JSON file will look something like, yeah, like a JSON file usually looks. It's basically a dictionary that somehow configures all the different modules that you saw in that previous slide. And it's also showed here how that is configured. So the file writer will take that and then it will know how it should populate the data sets and groups in the file, Nexus file. The problem is the generating these template files would be a tedious work. And why? Well, even the simplest case will result in files that are thousands of lines because there's a lot of brackets, there's a lot of new lines and so on. And it's really hard to just by looking at the JSON file to validate, okay, are we really following the standard specification that's available at this webpage? It's also kind of hard to verify, are the components correct in location? So is the chopper at least before the sample or is it after the sample? Well, you need to develop some plotting tools or use some third-party tool. Then you have another tool to take care of. And also people just generally use different type of libraries to generate these, or they might even write their own scripts to generate a lot of these JSON files. And we want to avoid that. So, and on top of that, sometimes you even need to go inside a file and edit that. And okay, should you edit the script or should you edit the file directly? So with the Nexus constructor, we remedy some of, well, all of these problems because Nexus Constructor has a proper but rather simple graphical user interface. It's developed in Python 3.7. It's using PySide 2 for the graphical components. We are currently upgrading to PySide 6. And you're able to see the whole Nexus configuration in a nice tree structure. And on top of that, you will have actually a rendering of components in a 3D view of choppers, detectors, monitors, and so on. It's really easy to load an existing configuration as long as you comply with what's reasonable for Nexus structure. And the definitions and documentation of the Nexus base classes that's retrievable from this web page for the Nexus standard is also integrated into the tool, so you have access to that directly. And the Nexus constructor in itself will do some sanity checks of the input you provide, data types, units, what kind of field name you're using in each group, and so on. And it works on Mac, Linux, and Windows, and it can be found in this GitHub link that's also provided in the presentation. And the UI is very simple. As you can see, there are like three main parts. There's to the right, the biggest part is the component viewer. So that when you start adding components and groups to the Nexus structure, it will render 3D objects here. And to the left, you see the Nexus tree on the lower left, and that will actually be the one you interact with. You will add groups, you will add data sets, and on top, above that, we also have some buttons to add transformations, add new groups, and edit current groups, and some zoom capabilities when we actually have some component in 3D rendering. And if we just want, so here's the demo part. If we just want to create a group to an existing NX entry, we can just click the add group, and there will be another window that opens up, and we can basically choose the desired Nexus class from a list that's directly retrievable from the Nexus standard. And these classes are split into groups and components. And the main difference between Nexus groups and components from our point of view is that the component has a physical property, either a shape or a location. And if we then hit and pick the NX sample, which is usually the Nexus class that's usually used to describe a sample, we will have the documentation next to the editor, and we can read the documentation and add the fields and attributes that we need to create a proper standard compliant sample. And if we start adding a field, for example, so in this sample, I just added a data set. I started writing a C here. It actually populates a list with suggestions that are following the Nexus standard. So we have a change of position, chemical formula, component concentration, and the red field here means that the value is not really, you need to specify a value and it needs to be a double. So here I added a chemical formula just to illustrate what it looks like to the sample, and that's all, no red flashing lights, so that's okay. I added a stream that's I'll explain later, and I just described the sample as like some kind of box, and I provided some dimensions here. And I added to the tree, and the tree will be populated with the corresponding Nexus classes. And to describe the geometry, it will follow the standard specification to create this shape I was defining in the box. And to the right, you also see like a small box, a very simple case. There are several ways to define these shapes. So they are, for now, we're limited to auto, box, mesh, and cylinder. And auto is basically custom shape for some specific components, such as beam choppers or slits. There are components that are configured like that. Nexus slit, Nexus detector, and the Nexus chopper will have an auto shape. And we will probably add more in the future. And please note that the sample, of course, is a component in this case. And we could also add transformations. So as I mentioned, the sample component has a location, so we were going to play around a bit, and I added a transformation, a translation, so we're moving it along the z-axis a couple of meters, and a rotation to the sample, and we can actually see it's updating, and we can do some sanity check. Okay, did it end up in the correct position? The same thing for really adding a beam chopper. You would usually in the Nexus standard, you would use an NX disk chopper. Then you would need to define the radius, some slit edges to define where the slits of the chopper are and how many of those you have, and the slit height. And then you can just describe the whole shape of the chopper. The same for slits. We use X gap and Y gap, and these are all compliant with the Nexus standards, these fields, and it will generate a 3D view of the slit, basically. And we can also add a more repetitive shapes. So in this case, I made like a small detector using an NX detector with cylindrical shapes that are aligned in just like a rectangular thing. And it's like a cylindrical pixel, basically. And you can then use the cylinder shape and define some repetitions of this shape. And that's basically your detector. But reality is never that simple. So we sometimes need to use more complicated cases. And that's when we enable the possibility, or implement the possibility to load off files to describe geometries. So this is a real example of such a case in the DREAM instrument that's being designed at ESS, which is a bispectral powder diffractometer. And this has several detectors with very complicated shapes. And here we just loaded off files and generated a file, added the choppers, added the monitors, the slits, everything. And it was quite less than half an hour of work to generate a compliant Nexus structure. I will also mention file writer modules. So we also stream data through using flat buffers. So really when we add fields to Nexus groups, we differentiate between three sets of types of data. It's data sets which are static data, for example, the chemical formula that I added in the sample example. Streams are all the dynamic data. So for example, the event data would use the EV42 schema at ESS, which is a schema we defined. We are currently updating those, so it will be new schemas as well. The chopper rotation speed would use the F142 schema. And there are also links to different other parts of the Nexus structures. Links, according to Nexus standard, is just pointing to, it's essentially a shortcut to other parts of the Nexus file, and that can be used to, for example, more easily retrieve essential data that you need quickly in the top layer of the structure of the Nexus file. And these are easily configurable. So the streams, you just, in the editor, you just edit it, and then you define your Kafka topic and Kafka source. Because we're using Kafka, that's the only way we have enabled to edit these, and you just add it. And the link is just basically as a data set, just adding where it should point at. And it does some validity checks of these that seem reasonable. And saving it is super simple. So when we're done, we just hit file, and there's an export to file writer option. If we want to open it again, we just open it, and that's it. And the summary is, well, as can be seen from this few slides, is that the graphical user interface, I would say, is very simple. You can actually see the different 3D components in the viewer, and you can at least do some initial validation of where things are located in the instrument. Complicated geometries, as for example with the dream detectors, can be imported as OFF files. And it's really easy to work in a group. I can save my JSON file, send it to you. You can continue if you're like a chopper expert and know exactly how the choppers look like. You just load the file and you edit it and send it back to me, or we can use GitHub or whatever means to version the files. As can be seen, we are integrating this Nexus class documentation and definitions from the standard specifications, and it will also give you some instantaneous feedback if you're not handling your inputs correctly in the fields. And yes, so as I said, this is an open source project, so you're very welcome to have a look at this link. It should be in the presentation that's uploaded as well. And that's my presentation.
Thank you, Kenan. Indeed, as you said, it's a very powerful and helpful tool for all of us who try to structure Nexus files programmatically.
Yes.
We have room for a couple of questions, if any. So there's one here.
Right, thanks. Nice talking to you. So will it also open an Nexus file if something else is doing it and show me what the structure is from the actual Nexus itself, or do you have different tools to actually look at Nexus files from different places?
So currently we're using another tool to view it, but I think the step to adding that wouldn't be too much. Well, it depends what you want to see. If you just want to, I mean, you could think about, okay, what template does this file that was saved use, right? Then you could easily just translate that into a JSON file if you have the correct attributes. But looking at the data in the Nexus Constructor is not possible.
So does Mantis, something like Mantis render these kind of?
Yeah, exactly. So no, but you could imagine at least, okay, these guys have this Nexus file. What did they actually use? The configuration file they use. So this is purely for building these configuration files. So it's not really a Nexus file constructor.
Yeah. We want to put more information in the Nexus file. So they can put locations, slits, and styles from source. We don't use in the analysis so much. Them having the way to visualize in the correct places, potentially really useful.
So basically data that they didn't save.
Yeah, so it's being recorded by a different instrument against the Nexus standard.
Okay.
But you can start to use them in the applications that we produce.
Yeah.
It's still kind of nice that they could open the file up and check the slits are actually where the slits are.
Maybe another question?
You said in the beginning that you were trying to follow Nexus as much as possible. Can you give any example of where you were not able to follow Nexus?
Yes, I mean there were so there were some optical components that were missing that we need for the neutron tomography instrument, for example, Odin that's being designed. But our aim is that we should basically get that into the standard and then comply with the standard. But yes, there have been. But I mean, amazingly enough, we managed to fix most problems.
Thank you again, Kenan.